you are all set, we can start. It's 2:30. We can start now, or should we wait? Bimalendu, should we wait?
We can start from my point of view if well, if
let's ask from the organizers if enough number of participants are there or not.
They are still. Let's wait another minute. I hope they're
yes. We can wait for a minute.
Yes. Yeah. Okay.
Okay, so
yeah, I think we can start now. So it's a pleasure to have Professor Esslinger again with us. So she'll be giving the second part of the lecture. This Bose-Einstein condensates meets cavity quantum electrodynamics. Okay, Professor Esslinger, please.
Okay, thank you. So it's a great pleasure to be here again. Of course, I hope to see you all. In hopefully not too distant future personally, and I hope that a lot of people of you will join and do research in the field, and I can read your papers. So that's would be really great. Okay, and if you do so and meet me at a conference, remind me that you had been here and that we've kind of met already. Okay, I would like. In today's lecture, we will do, we'll have a little bit more to do in theory, but not much more. And then I will show you how the experiments work and what in my mind, some key experiments have been. Of course, there's the focus on the work naturally that we have done. But the field is rapidly growing, and you can look at recent reviews, and there is a lot going on. Okay, so the setting is the following. We have we looked at, last time we looked at a single atom, and then we were inside a cavity, and we looked at how you have to treat that. And now we will look at a whole ensemble of atoms, and specifically a Bose-Einstein condensate inside a cavity. And we will look at mostly at the following configuration, that you have a pump beam, a laser beam from the side, which is back reflected, and which is off resonant with the atomic transition of the BEC, so maybe 785 nanometer, and then the atomic transition is 780 nanometers, and it is close to the resonance of a cavity mode. So that is the setting, and we will at this point now try to simplify to get the essence of this self-organization and, well, the somewhat surprising mapping to the decay phase transition. So what I will show you is that you can treat this as a spin system, a spin 1/2 system coupled to a cavity mode, which is the decay model. And it is a version of the decay model where you can actually see the phase transition predicted by Hebb and Lieb and questioned by other people, because for very strong coupling, the A square terms were neglected. Yet it was Carmichael who showed in a paper that in an open system you can actually realize it, and I guess the most easy way to realize was the way we did that. Okay, and a key point is the two-mode expansion. So the nice thing about the Bose-Einstein condensate is that it is a well-defined momentum state. It's actually a momentum zero state. And with the light field, it is coupled to well-defined higher momentum state. And it's actually coupled to one specific one. And that gives you a two-level system encoded in the external degree of freedom. So that in this two-mode expansion, coming from our general Hamiltonian we wrote down last time, we expand in the in the momentum zero mode and in a superposition of momentum states. We will come in a moment to see where how that looks like in a momentum picture. So the first, I mean, the zero state, momentum zero state, you just, for example, take 1 over the length of some volume or 2D volumes and 1 over constant. And the next higher mode is a modulated, cosine modulated, distribution. Okay, and what you have is that the atoms, you pump the system and you can scatter photons, scattering photons from the pump field into the cavity. Scattering of photons between pump field and cavity mode. That couples the two, couples psi 0 and psi 1. Okay. And now we can all briefly think what in momentum state, which momentum states do we actually couple? I mean, I've drawn almost everything here in momentum space, the momentum space diagram. This is supposed to be the momentum zero state of the Bose-Einstein condensate. And now we are wondering to which momentum states does absorption of pump photon and emission into the cavity, to which momentum states does that couple? That's, I mean, to get an intuitive picture. So you may, I mean, I will of course draw it in a moment. You might briefly think about it, and you may also, you're welcome to write it in the chat. So basically the question is, we have a Bose-Einstein condensate at zero momentum, that is here, and now it absorbs photons either from this side or from that side, or a superposition of those, and is scattering into the cavity. And now that means the atoms are coupled to another momentum state, and the superposition of this momentum state we want to look at. And I'm happy to see suggestions in the chat. I will have a sip of coffee and see whether there are suggestions. Okay, so then I will draw some. So here. Does that make sense? Yeah, exactly. Wonderful. Okay. Yeah. So the superposition, the correct one is, of course, you can absorb a photon and emit, or you absorb and emit. So you go absorb, emit, and then that you can do in 4 combinations. So you get into a superposition of, oops, that's wrong, of those 4 states. And now you can also imagine that that will give a density pattern. So you have the momentum 0 state, and then on top you have this psi1 state, and that gives a density pattern. And in real space, you will see that you do actually do Bragg scattering of this refractive index pattern. Okay, so and what we see now in this picture, if we neglect atom-atom interactions, and if we go into the basis that, say, this is spin down and the superposition of those 4 states is spin up, then we have a Dicke Hamiltonian. And then we have, in addition, a little bit of a dispersive shift, which doesn't, well, is like a constant, which just causes an overall offset, okay? Dispersive shift, small close to / below phase transition. When M, that's just a matrix element, it's roughly 1. Okay, and this two-level system, the transition frequency between the 2 levels, what is that? That one needs to keep in mind. What is this transition frequency? The energy difference between the 2 states. They have the same internal state, but they have different external states, and the difference in energy is 2 times the recoil energy. And now you see the trick why this is such a nice realization of the Dicke model, or the Dicke phase transition, because the Dicke phase transition basically says, well, what is happening if you drive a 2-level system so strongly that your vacuum Rabi splitting is as large as the separation between the energies. And here, if you choose the energy difference of your 2-level system really small, which here that's in the few kilohertz range, then you need a fairly weak coupling, again in the few kilohertz, to get into the regime of this phase transition. Okay, here we need to fill in that C0 are the bosonic mode operators for the Dicke model, and the total number operator is this. Okay. And okay, the ladder operator, I will just write it down. We need to speed a bit up. These are the ladder operators. And JZ you can also express in terms of the modes. Okay, and the collective coupling strengths. So since each atom, I mean, if you couple, you get a collective enhancement, because if you have a photon, each atom can absorb this photon, and that so you get the corresponding collective coupling. I mean, like having a huge dipole that is given by lambda. And the square root of n is the total number of atoms. And what is also important to note is that this Hamiltonian is invariant under a parity transformation. And that's, we will see in the phase transition, that is exactly the symmetry that is broken. Okay, symmetry, and we should write it down, symmetry spontaneously broken in self-organization. / decay transition. Okay, and now let me say a few words to the decay phase transition. That was suggested by Hebb and Lieb and Wang and Hio. Hebb actually, that is a nice thing when he turned, I think it was his 80th birthday, and then Lieb was also invited, and I had the pleasure to give a talk about their phase transition, which was of course a bit intimidating because they are of course kind of really big names in physics on the long-term scale. Okay, but it was nice, it was very nice. Okay, and they found out that the decay model displays phase transition, and then Carmichael, that is a paper which is also extremely important in this context. He realized that in an open system, you can actually create a model system that that realizes this Hebb-Lieb phase transition. Okay, and it's a second order phase transition to a superradiant phase. I mean, in terms of the Hebb-Lieb, what they looked at is in the end, imagine you have an empty cavity which is in resonant with a two-level system, and now you put a two-level system in, and then you get the vacuum Rabi splitting over the James-Cummings Hamiltonian. Now you put a second atom in, and then the splitting gets larger, and another atom, and more, and then your splitting gets larger and larger. And at some point they thought, okay, now if the splitting is so large that it hits the ground state, at some point there will be a phase transition that you suddenly have polarized atoms and a photon in the cavity, which is quite a crazy thought. For real two-level atoms in this very strong coupling regime, you would need another term, but you can, with quantum simulation approach, you can realize the original Hamiltonian that Hebb and Lieb looked at. Okay, and the critical, you get a phase diagram that is shown here, and let's put the axis. What is along the x-axis? That is the coupling. Lambda, that was a parameter I showed you earlier. And obviously here is some critical parameter where the system goes into a superradiant regime, where you have this polarization of the atoms and photons in the cavity. And this is plotted against the temperature. So you have this phase transition also at 0 temperature. And this lambda critical, that is square root of omega 0 divided by 2, where omega 0, that was the difference between the two levels. And that is a non-rotating wave, when you take into account the non-rotating wave terms. And the normal phase, there is Jz is 0, so you don't have an you have population only in the ground state, and no light, no field. And in the superradiant phase, you have J plus plus J minus are unequal 0. So you have a phase, you have a polarization, and the field is no longer 0. That is this phase transition. And now we will come to the PowerPoint part of my presentation, where I show you how one gets there experimentally, and how you relate that to supersolidity, and the most recent work where you look at where you have phenomena, dissipative phenomena, where kind of dissipation drives the dynamics of your system, where you get quite crazy systems that you can create out of well, this simple cornerstone of the Digger model. Okay, so I will now switch to the PowerPoint. Let's see whether that works. So I need to follow here. I'll stop share. I see you here, and then I would like to see the chat here. Okay. So if someone can, what is the order parameter here? Why is the x-axis? Why the x-axis is the temperature thing? No, the y-axis is the temperature. That's plotted against the temperature, and the order parameter is in the kind of out of the plane, and that is J plus plus J minus is the order parameter. That is kind of the checkerboard density. We will see that you get a density modulation, and that is and that is shown. And yes, the y-axis indeed, the y-axis is the temperature, and the third axis, the order parameter, and we will have that again in a moment, it goes out of the plane of the iPad. And that is, the order parameter is the J plus plus J minus, that is the checkerboard density. Okay. Very good. So it seems that there I can follow on my iPad the chat. That's good. And now let me share. Let me share the screen to look at the presentation. Let's see. It should be this. Share. Yes, that looks not too bad. And now I need to start the presentation. And yes, that seems also to work. So I'm quite glad about that. Yeah. Okay. Good. The chat I can see. I can see my presentation, everything. Okay, good. Please let me know if I don't react to your chat or something. You can also acoustically let me know if something is going wrong, and so I'll try my best to get the feedback. Okay. Okay, so let's have this picture again quickly. Okay, this was, we had in mind the BC in the cavity, and now let's go from inside out. That is the cavity again. We have seen this picture, and now how is the cavity inside the experiment? That is shown here. What we have is a magnetic trap, and then we have, let's see whether I can laser pointer Laser color, laser pointer. Okay. Okay. We have a magneto-optical trap, then we transport into a region where we create a Bose-Einstein condensate, and this Bose-Einstein condensate is then transported in a moving standing wave into this cavity. And remember, the distance between the mirrors was just 180 micrometer. So the focus of this is right in the cavity. And then it's loaded inside the cavity into a dipole trap. And then all the lasers are applied. So that's, and maybe for those who want to build experiments, here you can see how our design looks like. We have, it's a bit exotic design because we have an atomic source with a medium vacuum inside an ultra-high vacuum. So the bigger chamber is the ultra-high vacuum, and then from inside there is a not so good vacuum with a magneto-optical trap, but that gives us very short transport distances. And then there is a cavity here, and the whole system is cooled down to -80 degrees as to get good enough vacuum with all our coils and everything in the vacuum. But it works very nicely. And that's what it looks like from outside, and you see where the cavity is. Okay, and now let's see. This is the BEC in the cavity, 150,000 atoms typically, cavity length, finesse, we've had those numbers before. And now we shine a laser from the side, and then we increase the intensity. Now let's see what is happening. So we increase, well, there are some references, some additional reference to other people's work, which is important. But nevertheless, let's look now what is happening if you increase the intensity. Okay, so you increase the intensity. That was the horizontal axis in our phase diagram. Okay, you increase, and then at some point the system kind of decides to form a density wave, a spatial density wave, and scatter light into the cavity. And this phase transition is a competition between 0-point motion and the potential energy gained by the AC Stark shift. That's what it is. And now you can see here, you have the order parameter, that is the level. So the order parameter is now the y-axis. I think that's what there was a question earlier. That's what maybe is the more intuitive expectation for the phase diagram. So you have here the order parameter, and to the right you have the coupling strength. And at a critical point, the system starts to order, and it starts either to order in an even pattern or in an odd pattern. So this here is both kind of an illustration of the density distribution. So there are two types of modulations, either on the even or on the odd sides. You have to think of course, of a sinusoidal two-dimensional pattern. And on this, this is like a pattern in the refractive, in the superfluid refractive index. And now you can scatter light into the cavity from this pattern in both configurations. And the phase transition happens because at first the system tries below the threshold, minimizes its energy by delocalizing. So it has zero momentum and delocalizes. Above the phase transition, the system can lower its energy by coming up with a density ripple, but lowering its energy since there is an additional field in the cavity, which due to its AC Stark shift lowers the energy. So you have this competition between zero-point motion and potential energy that drives the phase transition. And now let's see what is happening. Okay, but if someone would show up on the screen, that would be wonderful. Otherwise, I feel I'm not talking to anyone, so that would be great. Anyone, whether student or organizers. Okay, so what is happening in the experiment? That is shown here. So the experimental sequence is that you produce a BEC in the cavity, and then you switch on the pump field and increase it linearly, the intensity of the pump field. And then you watch the number of photons coming out of the cavity, which is reflects the field. Okay, and that is shown here. So the time axis is here, and the photon number cavity is plotted in blue. Okay, so and then there's also, I mean, if you take a time of flight, though, you first see no Bose-Einstein condensate. Just a Bose-Einstein condensate. And then you increase the number, the intensity of your pump, that is the dashed line. And then what you see there, of course, because you have a pump field, you will get a little bit some Bragg peak. So you see that you have a standing wave along the pump direction. And now you increase further, and then you see in the photon number a sudden spike. So an increase in photon number, and if you that's done here, suddenly switch off your pump intensity and look at time of flight, then you see an interference pattern which corresponds to the self-organized phase. And then you can also check whether that is kind of a well-behaved phase. So here you see you have a time line where here's the pump power again, you increase, you keep it, and you lower it, and then you get into the phase and out of the phase. And this system, if you look at it with a condensed matter point of view, from a condensed matter point of view, then you can look at it as a lattice supersolid. And why a supersolid? The definition of a supersolid is that you have a combination of off-diagonal long-range order, which is basically you have a superfluid, and you have a non-trivial diagonal long-range order. So that's a density order. And non-trivial refers here to the fact that you have a density modulated wave function. Okay, there's a question here. Okay, very good. Very good. So first question is, what is the detuning of the light with the atomic transition? So that is a few nanometers. So probably we did that experiment. Typically we do them at 5 nanometers of resonance. So the atomic, the atomic decay is negligible. And then should I be thinking of this as a position space wave function or a momentum space wave function? Okay, very good question. It is a momentum space wave function. So what is done is in position space, you have this cosine modulation. You have that, well, you have the momentum zero state plus a modulation by this additional cosine kx times cosine kz. So you have a modulated wave function. And now this, if you Fourier transform it, or when you look at its momentum components, then you will exactly see this is the zero momentum component of the BC. And these four states are the superposition states in momentum space that we had discussed in the theory part. And these little peaks here, they come in addition, since the pump wave is also periodically modulated. So this is a momentum space picture. How is the cavity length stabilized? Okay, since it's a lattice momentum, by momentum, do you mean crystal momentum? Yeah. So here, yes, here the non-triviality of the diagonal long-range order is a breaking of the C2 symmetry, because you have two possible, so that's discrete, so it breaks a symmetry of the underlying mode structure. And here it's a discrete. We will see later that you may also break a continuous symmetry. But here it's a discrete, and that's why the adequate term is a lattice supersolid. So the system can find its structure either on the even or on the odd arrangement. And how is the cavity length stabilized during the experiment? That's a very good question. There is a super weak off-resonant field at 830 or 850 nanometer, which we use just for stabilization purposes, and which has causes a small modulation, small compared to all other energy scales. Very good question. Okay, and now you can look at it, yes, also as a phase diagram. And this phase diagram is now, you have the pump cavity detuning in the vertical axis and the pump power on the horizontal axis. And the third axis, that is the mean photon number, and the mean photon number is a measure of the order parameter, because the photons are scattered off the density modulation. You can theoretically calculate that you expect the dashed line for a simple model as the transition of as a phase transition. And here in the inset, you can see this diagram is made by increasing the pump power over time. And then, for example, here, this means this line here corresponds to that line. And then you start to see photons, and that is plotted in a color code here. So that's this line. And you see what a nice way we did in the paper. When we had taken the data for the paper, we didn't take the all the power ramp from here to there. So here there was data missing. We wrote it, of course, in the figure caption, but to make it still look nice, we thought, let's use this as an inset. Now it looks beautiful, and at the time we could send off the paper without taking the data again, and it looks nice. I'm still, one has to write it, of course, in the figure caption, but each time I see that, I still smile. But Christian Baumann, who sees this, that is, he then later took another time the whole phase diagram that you can see here. Okay, now one could say, okay, how do I discriminate between the two symmetry broken states? Because it's a momentum space picture, as was mentioned in the chat. And the two states can be distinguished by the phase, the time phase of the light, which is coming out of the cavity, and measured with respect to the pump light. And that we can do in the experiment. So we did an experiment where we measured the relative phase of the field coming out, the scattered field coming out of the cavity to the pump field. And for even, you have 0 phase, and for odd, you have a pi phase difference. Of course, there is one phase free, so you have the difference of the phase between even and odd is pi. Okay. And so what we did, so we set up such a measurement, phase-sensitive detection. And then we did the following type of experiment. So we ramp into the phase and out of the phase again, and that is shown here. And we measure this phase. And then we see, okay, if we are in the phase, we have a stable light field phase coming out. And now we do that several times. We go in the phase, out of the phase, in the phase, out of the phase, and so on. And then measure what type of phases do we see, phase differences. And here you see, we go in the phase, have a certain phase, then we go again into it, and then we have a pi difference in phase. So one seems to be even and the other seems to be odd. And then we do several times. And actually we did it kind of 10 times. And then several runs of going 10 times in and out. And then we did statistics on it and looked at what is, how often do you have even versus odd? Is there any preference or not? And if you take all data, then you have a preference for one. If you then take the data and how fast can we do this switching? How fast can we do this switching, phase switching? So here the time scale is in milliseconds. So we go in and out of this phase in this ramp, but we will also come just in a second in where we change the speed of this going into the phase and out of the phase. Very good question. Okay, but if we do it slowly in and out and take all data, then we have a preference of one phase. And then if we, since there can be residual light field scattering, and if we now take all post-select the data where we don't have in between our data sets, if we have a minimal photon number, so the cavity field goes down to below 0.02 photons on average, then we see a fairly balanced distribution. And then we can also do as a function, we can look at it as a function of a sweep rate. So, and that was exactly the question. If we go fast in and out of the field, out of the phase, so we kind of in a Kibble-Zurek manner, we would create a lot of defects. So we go in fast. And then if the faster we go, the better is our balance. The better is even and odd balance, which makes total sense. Because if you're fast, then you're on a higher energy scale, and any residual symmetry breaking field will not play a role anymore. So this seems to be very consistent also with a simple Kibble-Zurek picture for our our situation. Okay. Okay, and another thing that you can do is to probe the excitation spectrum. So one may wonder what are, and we've briefly outlined how you can calculate in general. But the question is, what is actually happening? How can you measure the excitation spectrum of this phase transition? I mean, in general, in a phase transition, you expect that a mode is getting weak until the phase transition happens. And in this case, it's the mode that gets weak is the energy difference between your two levels that gets weaker and weaker. So the effective level splitting, so kind of the dress level splitting, gets smaller and smaller. And if it touches zero, then you have the phase transition into your ordered situation. And what we can do to probe this phase transition is we send a weak pulse with a frequency difference compared to the pump pulse into the cavity and look at whether we can excite the systems. We can either watch the photons, but we can also watch the momentum peaks. And we can measure, we can then change this frequency or this delta here. Okay, let's see and measure, yeah. And these are data where it's shown. Here you see these Bragg peaks, and here you see the photon number after an excitation, and you see here the probe light of the field. And then you can, for the different regimes, so there's here it's a larger detuning, here is a weaker detuning where the resonance is, and you can now measure, change the pump frequency, and then you get a diagram as shown here. So you take different pump powers. So this is the axis. The lambda, and here is obviously lambda critical. And now you take these excitation spectra for different excitation frequencies. So, and they are between 8 kilohertz and 500 hertz. And you do kind of scans down there. And where you hit the resonance, that's where either with the atom data or with the photon data, we make here these data points. And then as we increase the pump power, we see a soft mode coming down in energy, and it comes down to 500 hertz. So that was in the minimum that we could see. And then we see beyond the critical point, it goes up in energy again. And they're also, I mean, in these dipolar systems recently, they have also measured such mode softening, which one can look at. So, well, we called it rotone type mode softening, but I expect that in Tilman Fast talk, you have heard a lot about that. Okay, so now you could say, okay, nice, but this is just a lattice super solid. We would like to see a super solid which breaks continuous translation symmetry. I mean, this is of course now a picture that was from Julian Leonhardt, so that who did contribute a lot to the work I will talk about in a moment. What was his kind of vision of a super solid. So you can see that it is somewhat still a bit super fluid, and it's cold, but it also has a periodic structure. Okay, so that's a possible picture of a super solid if you want to imagine it. But the breaking of the continuous symmetry, that means you may want a situation where you do not just choose between two density configurations, but maybe continuously, that the system, the crystal can form at any position. And this, well, is illustrated here by this moving pattern. And this one can achieve by using two cavities. One might at first think two cavities will just give you two Z2 symmetries. Yes, that's true. They give you two possible Z2 breaking of symmetries, but you can enhance the symmetry. And why you can do that, there is a fairly easy way to imagine. You can imagine that if your two cavities couple with exactly the same strength to your atom system, then there shouldn't be an energy difference whether the photon is in one cavity or in the other cavity or in any possible superposition. So you could have more photon in this cavity and less of the photon in this cavity, but that can continuously change. And if they couple both in the same way, if you have the required symmetry for that, then, and the coupling strengths, then you can continuously change the weight. That gives you a continuous symmetry. That's why it does make sense, even in a simple way. But you could also argue, okay, my complex numbers, they are exactly the same. You have the real numbers on the, say, x-axis, and the y-axis, you have the imaginary part, and you can construct any, well, you break rotational symmetry if you represent your number with an arrow in the plane. It's in the end, it's the same idea of enhancing this symmetry. Okay. How can you make these two cavities? Well, and they are both on piezos. That is a picture of the two cavities. And we have a new setup built a few years ago. And there you can transport the cavity setup into a high vacuum chamber. And it has a gate valve. So you have a load lock chamber. There you can bake out your system, and then you can transport it. And I have a little film to show you how that works. There is also some talking in mostly German when we made the film. So well, anyway, so let's start this film. I hope I can start it. Let's see. Yeah. So that is the sledge, which will be inside. This is the vacuum chamber at the time. Now there's, of course, masses of optics around it. That's Julian Leonard, who designed that mostly. Here you see the sledge where this copper thing which goes into the main chamber. That is the main chamber, and there are different contacts also for electrical connections. And now you can fix it with a screw so that it's rigidly held, so that there are not too many vibrations. So that's now fixed, and you can remove now this long rod, and and then it's in the sides chamber. Of course, here it's open. Usually we do it when there is vacuum. And now you can also get it back again. So that's the reversed process. Now you can change, rotate the screw again, you unscrew the sledge, it moves backwards, and then in a moment you can take it back from the science chamber in the load lock chamber where you can do the bake out. So yeah, there you see, so this is really cool. And now it goes into the other chamber. Yeah, there you see, now it enters the other chamber. That's where you can do the bake out when you put a new system in, and you can get it out. Okay, so that is this setup where Julian Leonhardt and Tobias Donner were the kind of the heads behind it. Okay, so let's move on to the physics of this. And as I said, we have two cavities now. You have more combinations on how the photons can be scattered. And you have this continuous symmetry. So let's have a look at the data. And what you see here now, these are phase diagrams which are arranged in the following way. You have the cavity detuning of cavity 1 as the x-axis, and the y-axis the cavity detuning of the second cavity. And why the cavity detunings? The cavity detunings, if I change the cavity detuning, I can change the coupling of the atom light coupling. So I have a continuous parameter with which I can change the atom light coupling. And this allows also to find where the atom light coupling of both cavities are exactly the same. And that is exactly the point where you then have a continuous symmetry, where you have this enhancing of the symmetry. And these plots are done in the following way. The light field is ramped up in intensity, and a certain one cavity is at a given detuning, and then the detuning of cavity 1, say cavity 2, is at a given detuning here, and then you you change the detuning of the other cavity, and that's shown here, and then you measure all the time what is the photon field in one or the other cavity. In one cavity it's red, in the other cavity it's orange. And here you see that if you get closer to resonance, which means you increase effectively the coupling, then cavity 1 fills. If you have if you go to another parameter where cavity 2 is much closer to resonance, then you already have filled the cavity 2 when you increase the intensity, and now you change cavity 1, and then you see that at some point the field in cavity 2 breaks down and the field in cavity 1 builds up. So these phases show you can have either field in cavity 1 or cavity 2. But there is also an intermediate regime here on this line where you have the same kind of, this line is more or less the dashed line of where both cavities couple with the same strength. So the question was, can I have a field in both cavities? Okay. And that is possible if you do it in the following way. You have the cavity detunings with the same detuning, or where they achieve the same coupling, and then you increase the intensity. And then what you see is that a field in both cavities builds up, and then you repeat the experiment very often, and you see always similar lines like this, but sometimes more field in the one cavity, sometimes more field in the other cavity, and that result is plotted here in this quarter circle. Okay, and there is a question on 3 and 4 wave mixing effects. There is, of course, an additional term. Once you have a stronger field, you might have scattering from one field to the other. But here we look at kind of the phase transition itself. At that point, these are negligible. But there are, of course, a whole range of additional effects that one can look at. Is there a phase relationship between the two fields in the cavities, in the two cavities? That phase relationship that we will have a look at in a moment. Yes. And depending on this phase relationship, you have a different pattern, and that gives you the relative phase between the two cavity fields, gives you the continuous symmetry, and that reflects in a continuous symmetry in your spatial pattern. It's a very good question. So this is like a coupling between the cavities mediated by the atoms. Yes, yeah. Yes, yeah, cool. Nice. I'm very glad about the comments in the chat. Okay, let's go to the next slide, and that shows you this enhancing of the symmetry. And here, and I mean, it actually goes directly to that question. So you have the two fields plotted here, and you have a relative phase shift, and depending on that, on the intensities of the fields. I was a bit unclear here. So the fields, and I actually might have given a not clear enough answer. Okay, so the fields to the question of the phase shift. Okay, so one has to think it in this following way. The driving field of the pump, that defines with you what your phase is with which the cavity field is driven. And that gives you only, in terms with a flexible phase, only a plus and minus sign, a Z2 symmetry. So the phase gives you only a Z2 symmetry. So that means with these fields, I can be on all of these possible 4 quarters of the alpha 1, alpha 2 representation of the field. Okay, can be positive, negative for both fields. So that's the Z2 symmetry. And now the continuous symmetry is the intensity of those two fields. I can have more intensity in this or more intensity in the other field. And this gives you kind of the amplitude of the projection on alpha 1 or the projection of alpha 2. And if you then plot the spatial distribution of the light intensity, then you see this corresponds to a continuous shifting of the interference pattern. And more precisely, and you can look at it as a free energy in this Mexican head. Okay, we'll come back to this Mexican head in a moment. Okay, and in the real space, you can look at the interference pattern here at different points of the circle that I'd shown before. And there you see this interference pattern. Say you look at this line here that shifts continuously. And the upper line, the lower line shifts just in the other direction, but it's a continuous symmetry. And you can also mathematically look at it to look at the Hamiltonian, and then you can show that there is a U1 symmetry in the system. Okay, And now you can also look at what are the excitations now of this system, which breaks a continuous symmetry. And here kind of there is a Mexican head illustrated, and we had early on seen this Mexican head in the alpha 1, alpha 2 plane. So the nice thing is that if we read out our field, we can directly read out the order parameter and the excitations of the system through the field. Okay, and now let's see what type of excitations can I have. I can have, for example, an amplitude excitation. So this excitation means that the total field in both cavities, if I add up, that they change their intensity, or they are both oscillating in phase, the intensity. Yet there is another mode possible, and that's a Goldstone mode. The previous mode is often also termed Higgs mode, and this is a Goldstone mode. So that's just a phase mode. That is the redistribution of photons or field from one cavity to the other. And that costs almost no energy. And that means you have an oscillation one field with respect to the other. So you could look at it in this way. You can describe it as well as an excitational amplitude or as a phase excitation. And now we can do the Bragg spectroscopy again, as we did with one cavity. Now we can do that for the two cavities. We can excite in both cavities, and then we can look at the energy spectrum. And that is what we see, okay? What we see now is, again, the modes, so these are in the two cavities, the modes come down in energy. And then, when we go beyond the critical point, we now have two modes. We have one mode which increases in energy again, and that's one would associate with the Higgs mode or the amplitude mode, and a lower mode which is the phase mode or Goldstone mode. Now you could say, okay, but what I see here is two modes. One goes up in energy and one stays low in energy. How should I know whether that's phase or amplitude mode? And the nice thing of our experiment is that we can directly read that out of our photon data. Okay, so for the Higgs mode, you would expect that both fields are modulated or both photon numbers are modulated in time in phase. So that gives you a total change in the field strength. And in the phase mode, one of the fields in one cavity would go down whilst the other one goes up. These are the two modes, and we measure those fields, and we can extract the phase, the relative phase of this modulation. And the data that is shown here, so the upper data shows the Higgs mode, and here you see that you have both cavity fields oscillate in phase, and you have the absolute value of alpha is modulated, whilst the phase stays fixed between the two. And here in the lower picture, and that's an excitation with the lower energy, because that's this low energy mode, there you see it after an initial decline in energy. Then there you see that the alpha is just declining a bit, but the phase is modulated. And that you can see here. Okay, so that's a rather direct illustration that you have this amplitude and phase mode. Okay, so now we come to another part, and I would suggest that we make a 5 minutes break, and then we have enough energy for a new part. And the new part, I mean, because you can see here, it's driven, dissipative, interacting quantum many-body system. And this sounds so awful because it's so complex, but you will see it's not so complex, because one has here something where the dissipation, you can actually associate with the dissipation a very characteristic feature. You can associate a dynamical instability with the dissipation, only due to the dissipation. And about this experiment, and that was the PhD of Nishant Dogra, I will talk about the break, after the break. Okay, so I will leave that here, and I will be back in 4 minutes. Okay, so see you in 4 minutes.
Okay.
Hi, I did not check the time now precisely. Am I too early now, or can we move on? Oh. Sorry, another 2 minutes, or how much is a BC mode, 0 mode depleted to get? So I'll answer the question now that is in the chat, and then we'll continue. So at the phase transition, it is it's at the very point when the higher mode gets populated. That's where the phase transition happens. So even if a tiny, I mean, it's of course the enhancement. You can also see that if you have a wave, a strong wave like the BEC, and then you have a tiny wave, only say a single atom or so, interfering with that, then you of course get a large interference pattern, and that's where the light will be scattered off. So it's at the very point that if an atomic field builds up, also the light field will build up. That's exactly the point. Very, very, very good question. And now let's move on, and let's look at this phase diagram, just that you see what's coming along. So this DM stands for density mode and SM for spin mode. So we will have two ways how to make a pattern in the system. And then you see here that is the plotted the difference frequency between the two modes, or between the squares of the two modes. So you have two modes which can get soft. We had described one, we had done this spectroscopy on the soft mode. So in this case now, we have a density and a spin mode which can go soft. And then we have a region where there's a dynamical instability, where the system will continuously flip from the spin to the density to the spin to the density pattern. And this flipping happens only because of dissipation. And that's exactly what Nishant Dokra had figured out, how to explain what we observed. So that was really absolutely great work. Okay, let's start.
There are some questions, Professor Esslinger, if you would like to take them.
Yes, sure. In the chat, or where are they? Because in the chat, I have answered the chat questions. No, there may be, I have not answered all. I've answered the last one. Okay. Okay, the previous to last. Okay, does any of this require a BC, or cold gases in the cavity, or a cold gas is enough? Also very good question. You have also this phase transition in a cold gas, but it's getting more complicated because you don't have the nice two-level system anymore. So and then you have to fight against a thermal energy scale, because depending on, you now have to think of superpositions of different kind of momentum families, and there you have to form a density pattern. But you can still imagine that in principle, you should be able to form a density pattern also in a thermal cloud, so it will still work. And there has been a very nice paper by Willi Zwerger analyzing kind of the multi-mode multi-momentum mode, which can then be generalized to finite temperature. I think with Philip Struck, the work was to look at the finite temperature. And there had been work prior to our decay phase transition in Vladan Vuletic's lab, where they looked at the thermal cloud and could see that there is a form of self-organization. And so this is like a coupling between cavities mediated by the atoms. Yes. And is there a phase relation? That I had already answered? Okay, good. So I think the questions I've answered. And then I'll move on with the dynamical instability. And for this, we have to look at one additional thing, and that is what is happening if we change the spin polarization of our pump laser. And that is illustrated here. And then one could argue, okay, that only is relevant if we also have different magnetic sublevels, but those one can have, and we look at magnetic sublevels, MF equals 0 and plus minus 1. Okay, so and now you imagine you change the angle phi of your polarization with respect to the y-axis. Okay, so and let's see what's happening. So if you have normally linear polarized light along the y-axis, as we had done in the previous experiments, then you scatter. Well, the atoms, you can imagine they are scattering like a dipole into the cavity. So it couples to the cavity mode. It's different if you drive a dipole pattern along the x-axis that will not couple to the cavity. Okay, but that's not the end of the story. I mean, you can, of course, look at your linear polarized light as a superposition of sigma plus and sigma minus light. And let's assume we apply along the light propagation direction, a magnetic field. And we look at all three different magnetic sublevels of the F=1 manifold at a fixed finite magnetic field. And then we will see that the coupling to sigma minus and sigma plus is identical only for the MF=0. And then you could get an oscillating dipole which will not scatter into the cavity. It's different, however, for the MF=1 and the MF=+ state. And those will give rotating dipoles. And they will also give a phase shift in time phase of the light field. And you can also look at it as a scalar dipole moment plus a vectorial component. Okay, let's now look at that. Well, that is basically summarized that if you have MF=1, MF-1 or +1, you should be able to scatter. And now we did that in the experiment. So what's shown here, the normal linear polarized along y-axis, and we look for the these are the phase diagrams as shown before, detuning versus pump field, and for the MF=+1, 0, and -1 a sublevel. And now we change the polarization. And then we see at 75 degrees, we still have fairly, I mean, these phase diagrams on the left, they looked all basically the same. Here, we see that we can self-organize quite easily the MF=+ and the MF=-1. Yet, the MF=0 is much more difficult to self-organize. You need much more power. And if we go to 90 degree, the MF=0, as we had expected, will scatter just in the wrong direction and not self-organize. Whilst the MF=+1 and the -1 will self-organize. And they will self-organize with different phases of the scattered light. And this phases of the time phases of the scattered light, which one can measure in the output of the cavity, they are shown here. Okay, and if you have a 90-degree phase shift if you are at a 90-degree polarization. And of course, for the MF equals 0, we can no longer measure because there's no light coming out, because there was no self-organization. Okay, you can also do that in a spin mixture. And then let's focus on the spin mixture of MF equal +1 and -1. And then you get a phase diagram shown like here. So here we have the parameter on the horizontal axis is this angle of polarization. And then we see that we can associate in this regime, if we have an angle below 60 degrees, then we can associate what is happening in the system is a density pattern forms. And the density pattern forms in such a way that both MF equal plus and MF equal -1 are sitting on the same sides, on either the even or the odd sides. However, if we go to an angle, say above at 70 degrees or something, then we get a spin texture, and then the spin down sits, say, on the even, and the spin up on the odd sides, or vice versa. And you can look at that, well, in this way. Okay, so, oops. So you can look at it as light in the vertical direction is a pump light, and it will be backscattered into the cavity, okay? Well, because here there's higher density, there's this modulation in the refractive index. And this is distance here is lambda, so you will constructively interfere. And now, well, you would say if this is just density, then it would not constructively interfere. However, you have the phase shift between the driven dipoles. And due to this phase shift, since the spin up and spin down are 90 degrees out of phase, you again get constructive interference scattered into the cavity mode. Okay. However, your mode, you couple with the two different, in these two different situations, you couple with different quadratures of your light field. Okay, so in a simplified diagram, it's the following. You have a Bose-Einstein condensate, which in a superposition of, in a mixture of a spin up and a spin down state. And you can couple this with one quadrature of the light field to the density mode, and the other quadrature of the light field couples to the spin mode. If you go very much kind of in one spin, in one polarization of your driving field, you're either here or in that situation. Now the question is, what is happening if both these modes are getting soft? You couple to both, and then they seem to compete. There something must happen. Both are getting soft at a certain angle of polarization. And that's what we looked at. What's happening there? And one would say, oh, these are orthogonal. Nothing will happen. If it comes from that side, it will stay there. If it comes from that side, it will stay there. But that's not the whole story. The whole story is that those two modes are coupled by the cavity dissipation, because the cavity dissipation leads to a phase shift of the field inside the cavity, and that couples those two modes. So the dissipation here leads to a completely different phase diagram. That's just to a little shift of something, or but it leads to a new phenomenology. And in the slides you will find, since the time is passing quickly, I think. I will not go through this Hamiltonian. The basic point is you have a coupling to the density mode and the spin mode, and one time the coupling is the one quadrature of the light field and the other quadrature of the light field, and you have with plus and minus the two spins indices. And you have here the density mode as an order parameter or the spin mode as an order parameter. And you can adiabatically eliminate the phase, and you can solve what you get then when you do that is the following, that you get a regime where your system is in time driven from the density mode to the spin mode to the density mode to the spin mode and so forth. And that's what we also had observed. Actually, we had observed it, and then we needed to think, Nishant thought, and Manuele Landini and the other co-workers, how to interpret that. And here we can see that this motion in between the modes, that pops up in the phase, in the time phase of the cavity output field, which is plotted here. And that is running, and that is shown here. And you can also here see on the left, that is the normal self-organization in the density mode. And here, this middle and the right picture is if you have this self-oscillation between density and spin mode. And here in the middle, it's when you have actually a dissipative kind of a locking between those two modes. And then you can you get this phase diagram, which I briefly had discussed. And here, as a function of polarization mode, here you see the modes and the locking of the modes. And here you see that the mode that is oscillating has a gain. And you can also get into a regime where you have a kind of a limit cycle where there is a fixed indication of a limit cycle where we have it's oscillating at a fixed frequency. And one can associate that with mechanical forces. I will just give you, that is the last slide I will talk about. That is the mechanical analogon to what we've seen here. So imagine you have a shaft, that's this outer circle, filled with a hydrodynamic medium, okay? And now you have a disk which is rotating, okay? So the disk is rotating, and that will lead to friction forces with this hydrodynamic medium. And it will leave, if you start rotating at the center, then you have an instability. If you slightly go away from the center, since it's a hydrodynamic medium, you will have a larger velocity here and have a larger friction force here, which will give you a total force, the friction force, upwards. And this friction force is position dependent and not, as we often associate, velocity dependent. And on this previous view graph were the different mechanical forces and how they are categorized. And this position, non-conservative positional force, that is analogous to our in our observation. And what I'm not going to talk about now, which is again a big field of research, is that if you look at a lattice model plus the long-range orders, which is of course super interesting because there you have a competition between the atom-atom interactions. They can be on the same energy scale as the long-range interactions. But that would be too much. And here's a phase diagram. But what I would like to think here is the current team. Since due to the corona, so that's not, again, not the latest team, but you see here that is Nishant, Dokra, then Manuele Landini, both worked on the cavity, and we have also Tobias Donner, of course, he is a senior scientist in my group, and also on the cavity, Francesco Ferri and then Rodrigo. And up here you see the impact team where Tobias Donner and I are co-PIs, and the team of that experiment, that was the two cavity team. With that, I would like to thank you all for joining the lecture. And yes, I hope you enjoy the rest of the school, and I hope that, yes, we will meet in person at some point, and hope that you'll...
Thank you so much, Professor Esslinger. And there may be some time for quick 1 or 2 questions, if there are any from the participants. You can post your questions in the chat box. I was reading that review article which you suggested in your in your talk, those references, and they sometimes use this confocal cavities, which is known to be unstable. In what context they use this confocal cavities and unstable cavities?
Yes, there is concerning these cavities with many modes. There is work in Ben Leff in Stanford. He is looking at that. And I think the challenge there, I mean, it's very nice work. The challenge there is that, of course, if you couple to many modes, you couple weaker to each of the modes. So you are in a regime, well, where you have to compromise a bit more on other heating rates. But I think it's a very interesting approach to look at several modes, and be it, well, there are different ways how you can produce many modes, but surely that's a very interesting approach. Yeah.
There's another question from Saikat. So it's in the chat box. You can look at the chat box.
Is the cavity output oscillation N equal between the SM and DM phases? Are also due to these being super, so due to these being separated phases. N between, is the cavity output, I need to understand what's been asked. Output oscillation N between the...
Yeah, and maybe I can ask directly. Yeah, I think that equals the typo that might create confusion. So I was asking that when you detect from the cavity, the SM, the spin, and the dissipative modes, are they like super and subradians, and that is why you see the cavity, that oscillation? Are they like super and subradians, and that is why you see the cavity, that oscillation?
So I'll go back. Maybe let's see.
Now let me rephrase the question. What Saikat is asking, that those two modes, spin mode and the density mode, yeah, can you consider them as the subradiant and superradiant states? Is that the question, Saikat?
Yeah, that's the question.
Okay.
I guess that's the question. Let's see whether you can rephrase it. I need to think whether the rephrase. I have a problem here with my. I think my computer is
okay. What I suggest, Saikat, you can get in touch over email with Professor Esslinger and clarify this point. Okay. So let us thank, since because of constraint in time, let us thank Professor Esslinger for excellent lectures. And we do hope that in future activities, you would be physically here, or at least online, you'll be joining us again in future. So
yes.
looking forward to all
so,
that.
Yeah,
Thank you.
It
again.
was a great pleasure. Thanks very much for the invitation. And I think it's great that you organized this whole school. I think that's really, really great. And I saw also that the community, that so many people joined in, that's really great.
Yeah.
Right.
Thank you.
Okay, thanks a lot.
Thank you, Professor Esslinger. And also thanks to Professor Shoshi Dattagupta for chairing the session. The next talk will begin at 4:15. So we have about 3 minutes, 2 to 3 minutes time.
Okay.
Okay, so I say bye. I stop sharing and I leave. Okay, bye.
Hello, this is Shubhodip from IUCA. Is anyone from the organizer there? Like Bimalendu?
Yes, Shubhashish. Yes, Shubhodip. Yes,
yeah,
I'm here.
Yeah. So shall I start at 4:15, or there will be some indication from your side? So is
no,
the
you can start.
Is the speaker already here?
Let me check.
I don't see his name in the participant list.
Is Kabusri there or Gopi?
Hello.
Hi, sir. Hi,
Yes,
sir. Yes, sir.
Speaker is joined. We have given the co-host.
Yes, sir. He's here. He's a co-host.
Oh yeah, I see him.
Yes.
Hi Christian, this is Shubhodip. Hi. Do you want to check your the sharing options and etc.?
I beg your pardon?
Will you please check the sharing option, sharing of your talk and
Yes,
screen?
yeah, I'll do it. Just a moment, please.
Yeah.
Okay. Is it fine?
Yep. Can you just click one slide next so that we can? Yeah. Perfect. So Christian, just one thing I like to ensure, like, would you like to get some questions in between, something, let's say on the midway, or all the questions should be asked at the end?
I'm fine for having midway questions.
So maybe can you just give a pause somewhere, wherever you feel it is right, something like in the middle or something like around that, so that we can get few questions and
yes,
then remaining at the end.
Yeah, okay, fine.
Yeah, great. Thank you. So it's already for 15 minutes past 4. Shall we start, Bimalendu then?
Fine.
Yes, you can start. Yes.
Yeah. So
okay.
welcome once again to this ICTS organized the school for trapped atoms, ions, and molecules. I am Shubhodip De from IUCA, and I will be moderating this session. And there will be 2 talks by the speaker, Professor Christian Roos. So actually, before I start introducing the speaker, let me thank the organizer like Bimalendu, Sourav, Dutta, and Saikat, Ghosh, who has organized this fantastic school, which is really very nice, and it will build up the community in India. Today, Professor Christian Roos from Institute of Experimental Physics in University of Innsbruck. He works on ion trap systems. He will give 2 lectures today and tomorrow at the same time. Today is the first lecture by him. So just a brief introduction about him. He obtained his PhD in 2000
His thesis was under the supervision of Professor Rainer Blatt at University of Innsbruck. And then he went for a short postdoc at LKB, worked with another stalwart, Jean Dalibert there. And since 2002, he is a permanent faculty at University of Innsbruck. His research interests are on quantum optics and quantum computation simulations using trapped ion systems, and also precision spectroscopy with lasers. And he has several experiments ongoing there in University of Innsbruck, particularly on quantum simulations, quantum logic spectroscopy, and also new things like using picosecond laser, showing some gate operations and so on. So, so today as we see the title of the talk, that entanglement in trapped ion systems. So now I request Christian, so it's over to you.
Thank you for the introduction, and thanks for the invitation to giving me the chance to talk about our research and the research that is done in a wider community worldwide. Originally, I had planned to spend today's and tomorrow's lecture on the topic of quantum simulation, but after having seen the slides that the other speakers on trapped ions presented, I thought I should try to make it a bit more general, at least in today's lecture. And so I changed the title into Entanglement in Trapped Ion Experiments. And so you've already had a couple of talks by Dietrich Leitfried, Markus Henrich, Stefan Village, Jonathan Home on trapped ions. And I want to fill in some more details and focus on a particular subset of topics. So in general, I mean, I'm going to talk about quantum physics with trapped ions, which is not a very new topic, which is has been around for a couple of decades. And in the beginning, this research has focused on experiments with single ions and efforts to turn these ions into an extremely well isolated quantum system that can be controlled and then used for a couple of applications, such as frequency standards, where you can think of single ion optical clocks, or for precision spectroscopy, for example, in penning traps, with measurements precision measurements of the mass of trapped particles or of the G factor, but also in quantum optics, where trapped ions have proved a very nice model system for studying topics such as quantum jumps or anti-bunching of light emitted by ions and so on. Over the last 2 decades, with the advent of quantum information, the focus has shifted a bit on experiments involving more than just a single ion. And instead of working with single ions now, people are very interested in working with ion crystals and also turning them into an isolated but also a complex quantum system with applications in quantum computing and tests of quantum theory, quantum simulation, quantum networks, but also using entanglement that can be generated among the ions for quantum metrology and precision spectroscopy. And so what I want to do today and tomorrow is to focus exactly on this aspect, having ion crystals as an isolated complex quantum system with which can be used for experiments in quantum computing, quantum simulation, and also with experiments that can investigate what kind of entangled states are produced in these experiments and what methods exist for characterizing them. So my outline for today is to talk about trapped ions as an interacting quantum system. And I want to talk about the properties of ion crystals. That's something that Didi Leibfried already mentioned to some extent. And also about then advanced laser cooling techniques for preparing these ion crystals at low motional energies. I want to spend a bit of time on quantum control of ion strings that are in experiments, before I then will discuss what kind of entangling interactions exist for entangling the internal degrees of freedom of an ion crystal. And I will finish with with a few words about gate-based quantum computation. But let's start with a look into a lab where a quantum simulation experiment is carried out. And you can see here the hardware that is needed on 2 optical tables. And this hardware consists, on the one hand side, of the ion trap. I hope that you can see my cursor here. If not, maybe someone can raise their hand or make me aware that this is not working. So you can see here the vacuum system housing an ion trap apparatus for trapping ion crystals. And on the other hand, we have lasers on the optical tables and the optical elements that are needed for shaping laser pulses that are sent to the ions. And lasers are very important for these experiments in various ways. In the first place, they help us to create ions by a photoionization process, maybe laser ablation for producing neutral atoms crossing an ion trap. We use lasers for laser cooling so that we can describe the ion motion as being quantized. We have used lasers in many experiments for coherent excitation and, most importantly, the generation of entanglement. And finally, lasers also play an important role in the quantum measurement process because we use the fluorescence that is by lasers that are excited by ions excited by lasers for determining the quantum state of an ion. The ion trap, on the other hand, is a great tool because it enables us to load ions just within minutes into this trap. And this is a short time compared to the storage time, which can be on the order of a day or days even. And this has to be compared now to the duration of an individual quantum physics experiment, which typically is on the order of 20 milliseconds and which comprises the initialization of the ions, the coherent interaction, and the measurement. And if you compare these timescales, you can see that over the course of a day, we have now the possibility to carry out something like maybe 10 to the 5 to 10 to the 6 quantum measurements per day with this apparatus. Now, this is quite a lot if you compare it to the experimental repetition rate that you have, for example, in neutral atom experiments. It is a number that is quite a bit smaller than what you have, for example, in experiments with superconducting qubits. But with 10 to the 5 to 10 to the 6 quantum states that you can produce, there's already a lot that you can do. Now, let me also discuss a bit the length scales that we have in our experiments. So if you trap an ion crystal like the string that you can see here, we need some anisotropic trapping potential in which the ions are harmonically trapped. And typically the trapping frequency along the weakly confining axis is on the order of a megahertz. And this frequency scale sets then the length scale for the distance between ions. And typically this is on the order of about 5 micrometers. And it is, in this sense, the largest length scale that we have in our experiment. It is quite a bit bigger than the laser wavelengths that we use for manipulating the ions. And then there is another length scale that is of interest, which is the length scale to which we can localize ions by laser cooling, which is on the order of 10 nanometers. And finally, the smallest length scale in our problem is the Bohr radius, which determines what is going on at the level of atomic interactions. And you can see that we have a good separation of these length scales. This is interesting for a couple of reasons. It is very helpful because you can see that the ion distance is much bigger than the laser wavelengths. And for this reason, it is possible to record the pictures that you can see here by spatially resolving the fluorescence emitted by an ion. And this way, we have the possibility to carry out measurements on individual ions and not just on the ensemble of ions that is trapped in our trap. Secondly, this separation of length scales is of interest because it means that we can strongly focus a laser beam to a waist such that it interacts with just a single ion in the string and not with all the ions at once. And so this provides us access to individually addressing ions, quantum control over individual ions in the string. And finally, you can see that there are many orders of separating the ion distance from the Bohr radius. And this is good and bad at the same time. It's good if you want to treat the ions as a quantum memory. In that case, you don't have to worry about changes of the quantum state of one ion that might be caused by another ion being in a particular other quantum state. But it is bad if you want to realize entangling interactions between the ions because it means that there are no directly naturally occurring state-dependent interactions between the ions. You just have the Coulomb interaction. And in that case, one has to think about how to engineer interactions which enable us to produce quantum correlations between the internal states of the ions if you want to treat the ions as one big quantum system. Now, I told you we would like to use ions as carriers of quantum information, and so we would like to encode a quantum bit in the electronic states of an ion, and try to isolate these quantum bits from their surroundings as well as we can. And that's something we will achieve to some degree. I mean, there's always the rest of the world in the sense that we have an experimental apparatus which we use for trapping the ions. And then there's, of course, always the risk that there might be decoherence. And if we design the experiments in the right way, then we have just a fairly weak coupling. And our goal is now to have, on the one hand side, switchable couplings to our experimental apparatus, which provide us with the control that we need. And on the other hand, not to lose the coherence by having undesired couplings or couplings that we cannot really control. And then the question arises, how can we achieve a coherent coupling between the qubits? And there are several possibilities. I think Markus Henrich is going to talk about, or has, I'm not sure if he has talked about this already, about using Rydberg interactions that provide a direct coupling between the ions. Or the other possibility is to make use of another quantum system that might mediate in an indirect way the coupling between the ions, or it might be a quantum system to which a particular ion is coupled, and that can be then used for producing entanglement. And that's something which Markus Henrich discussed, I think, already when he talked about coupling ions to photons, where this harmonic oscillator might represent now maybe the mode of a cavity. On the other hand, you can also think about the collective mode of motion of an ion crystal that can be used to induce entanglement between the internal degrees of freedom between our ions. And that's something I will discuss today. Okay, so what is needed for our experiments? We want we have to talk about some decoherence that might occur in our experiments. And there's a list of topics that I want to list here, and that's something you should have in your mind, because I will not make any particular reference to this, but that is something that needs to be controlled experimentally. So in the first place, we of course want to avoid ion loss by collisions with the background gas, and for this reason we try to have a very good vacuum in which we trap our ions, so that we have only very infrequent collisions that either, if they're benign, they just heat up the ion crystal and might give rise to a melting of the ion crystal. But if they are energetic and if we are unlucky, then it could also be that we have chemical reactions so that atomic ions are converted into molecular ions, for example, that are not useful for our experiments. Then we have to consider motional heating by fluctuating electric fields, as well as motional dephasing, and I think Jonathan talked about this a bit in his lecture. Then there can be decoherence by spontaneously scattered photons that might destroy the quantum coherence that is inscribed in a superposition of electronic states. We have to consider dephasing by fluctuating magnetic fields and laser phase noise. And for this reason, we want to have, in some experiments, extremely frequency stable lasers, and we will try our best to either pick electronic states that are not sensitive to fluctuating magnetic fields, or to control these fluctuations by using mu metal shields, for example, in order to reduce them as much as we can. Then there can be decoherence by fluctuating control parameters, like, for example, the laser intensity or the direction to which a laser is pointing. We can have decoherence that is induced by the ion motion, and this is the reason why we would like to cool the ions to temperatures as low as possible. And finally, we also have to take into consideration the disturbance by the time-varying fields of a radio frequency trap if we use an RF trap and not a Penning trap for trapping particles. So in summary, what we need is ultra-high vacuum, stable lasers, and many, many feedback systems for keeping these parameters at a relevant state. Now, there are different types of ion crystals that you can create in ion traps, and the ion configuration that is created depends on the ratio of trapping frequencies. And here I assume that the ions are trapped in a harmonic trap, and so that I can describe the trapping potential just by specifying the 3 trapping frequencies along the 3 different spatial directions. If you have a potential that is very anisotropic, such that you have a weakly confining direction and 2 strongly confining directions, then the minimum energy configuration that the ions take on occur in the form of linear ion strings. Secondly, we can have 2D structures in the form of planar crystals. If you have one direction which is very confining as compared to the other 2 directions. And finally, you can of course also have 3-dimensional structures if the ratio between the trapping frequency is not as extreme as in the other 2 conditions, or if you have many ions that you put into such a trapping potential. And this can be advantageous, for example, if you would like to work with as many ions as possible. Now, in a bit more detail, the ratio of trapping frequencies determines the crystal structure, and an important parameter is the anisotropy parameter, which is defined in this case. And here I discussed just the case of a trap which has some rotational symmetry, so that you have maybe one particular axis with an oscillation frequency omega z, and in the 2 directions perpendicular to this direction, you have the same trapping frequency, which I call here omega perpendicular. And you can see in this diagram that the crystal configuration that is taken on depends now both on this anisotropy parameter, but also on the number of ions that is trapped in the trap. So if you have an isotropy parameter that is quite small, which means that there's one direction which is weakly confining compared to the other directions, then you can see that we have as a stable ground state configuration a linear ion crystal. And if you start now adding more and more ions to this linear crystal, then you can see that at some point, this is plotted on the right-hand side, the ion crystal starts to explore a 2nd dimension. So it becomes then takes on the form of a zigzag crystal, which starts to grow until finally you get into configuration where the zigzag crystal turns into a helix. And the same is true if you increase, actually this is what is shown here. If you decrease the anisotropy and go to, if you increase it and go to bigger and bigger anisotropy parameters, and then you cross this diagram here where you go from a linear configuration into a zigzag crystal into a helix. And then if the confinement becomes very strong along this particular direction, then you squeeze the ion crystal such that it forms a planar crystal in this perpendicular plane. And now, if you have ion strings in linear radio frequency traps, that is, this is an interesting configuration, the linear trap, because you have in this case a 2-dimensional radio frequency quadrupole. This means that that there is now a line in space along which the radio frequency field vanishes. And if you have, let's say, a weak confinement along this direction, then it is possible to form linear ion crystals along this line, and you can confine them in this weakly confining direction by a DC electric potential in such a way that the ions are all located at places where there is no micromotion, that is, where there's no driven motion that is induced by the strong electric time varying fields of the trap. And this is why linear strings of ions are an interesting object for quantum physics experiments with multiple ions, because they can be placed at locations where they don't undergo this micromotion, which might otherwise perturb the experiments. Now, let's talk about linear strings. I told you you have now the equilibrium positions are now fixed by the trapping frequencies. And then secondly, you can be interested now not only in the equilibrium positions, but also about in the motion of ions around the equilibrium positions. And this is completely analogous to what you have in solid state systems, where you have the vibrations of the crystal lattice around the equilibrium positions. And it means that for the linear strings, you can describe the ion motion in the limit of small oscillations by a set of collective motional modes. And for linear strings, these collective motional modes decouple into a set of motional modes that describe the motion along the axis of the ion crystal, and into two other sets of modes in the transverse direction that describe then the ion motion along one transverse direction and along a second transverse direction. And it is straightforward to calculate these oscillation frequencies. And because of the role of the Coulomb interaction between the ions, the oscillation frequencies are not the same, so they're not degenerate. And what you can see here is a plot of the axial modes of motion, starting from the lowest frequency mode, the center of mass mode of motion, which is well separated from the next higher mode of motion, which is the stretch mode of motion, where the ion string expands and contracts along its axis, and then higher order modes, modes occurring at higher frequency, which describe then the shorter wavelength excitations. And then on the other hand, you have a set of modes that describe the ion motion in the transverse direction, starting with the highest frequency mode, which is once again then the center of mass mode of motion, and then the next lower mode is a tilt mode of motion, and then you have a bending mode of motion, and then you have once again shorter wavelength modes. And these can of course overlap. In this case, the parameters are chosen such that they are separated in frequency, but they don't have to. And so this is an example, for example, of a center of mass mode of motion, where the ions were excited by modulating the external potential to undergo this center of mass mode of motion. And then you can see that you can also, by modulating the potential, excite the stretch mode of motion. Of course, if you see the ion excursions, then here clearly we are not in the limit of the small excursions for which this linearization of the forces is valid. And so the separation of this center of mass mode of motion of a linear ion crystal is interesting, because in this case you have a mode that is well separated from other vibrational modes of motion. And if you're interested in coupling just to a single harmonic oscillator, then this is a mode that is useful to consider. On the other hand, if you are interested in coupling to many oscillators at the same time, then the radial modes are of interest, because they tend to cluster in frequency space. So if you have very anisotropic potentials, or the more the potential becomes isotropic, the smaller the frequency range over which you find these radial modes of motion. And as you will see later on, it is possible then to have lasers that couple to these radial modes of motion in an interesting way. In the case of a planar crystal, you again have collective modes of motion, but this time you have now two sets of motion. There's one motional mode set that describes the vibrations of the ions in the plane of a planar crystal. And then if you have n ions, there are n out of plane modes that describe the motion perpendicular to this plane in which the ions are located. Now, so let's talk about quantum control of long ion strings. And in the following, I want to discuss first some laser cooling techniques that you can use, which were not really covered by Dietrich Leibfried's lecture. He talked briefly about ERT cooling, but I would like to talk about this in a bit more detail. And I also would like to mention another laser cooling technique that allows you to cool below what is possible with Doppler cooling, and that is polarization gradient cooling. Next, I want to talk about techniques for controlling individual ion qubits, and about quantum measurements that we can carry out on these ion qubits. And then, importantly, I want to spend more time on discussing entangling interactions that we can engineer by laser pulses that couple to the motional modes of motion. And here I want to discuss the so-called Murmer-Sørensen interaction, and also some other so-called geometric phase gates. Okay, So yeah, so let's start with laser cooling. And I prepared here a little table to show you that different laser cooling techniques exist, and for good reasons, because there are different metrics that you might want to apply to a laser cooling scheme. And like, for example, you might want to know, or might be interested in achieving just the lowest possible final energy of an ion after having laser cooled the ion, or you might want to have a laser cooling scheme that is good for cooling ions that are initially at a high temperature, because other schemes might fail in this case, or you might be interested in having a scheme that is enabling a very fast cooling, or you might want to have a laser cooling scheme that is good at cooling vibrational modes of motion of an ion or of an ion crystal over a wide frequency range. Because as you have seen, and these collective motional modes occur over fairly different frequencies. And which are laser cooling schemes that are good and bad in this respect? Doppler cooling is well suited for cooling ions that are initially hot. It has a high cooling speed, and also the frequency range is very high. The only drawback is that the final energy is not so low. And typically with Doppler cooling, you are able to cool ions into the lamp decay regime, or close to the lamp decay regime. That is, you can localize ions on a length scale that is either comparable or small compared to the wavelengths of the laser light that is being used for laser cooling. But you will not be able to Doppler cool ions to the ground state on the typical transitions that are available in trapped ions. For this, it's much better to use resolved sideband cooling, which enables you to cool ions really to the motional ground state of the quantum harmonic oscillator describing the ion motion along one direction. But this is a scheme that only works if you start out already at fairly low temperature. The cooling speed is not great, and also the frequency range of modes, that can be cooled at the same time is rather small. So this means that if you want to cool one collective mode of motion, then typically you have then to cool one mode first, and then to detune the laser to change laser parameters to cool maybe a second collective mode of motion to the ground state as well. A related scheme is cooling by electromagnetically induced transparencies, which also enables cooling to the ground state, and which has improved characteristics with respect to the cooling speed and the frequency range over which you can cool. And finally, as a complementary scheme, there's polarization gradient cooling, which provides you with a sub-Doppler cooling. It works as the other sub-Doppler cooling schemes, only if the initial temperature is not too high, but it has a very high cooling speed, and also the frequency range over which you can cool modes simultaneously is quite large. And for this reason, I would like to spend a bit of time on ERT cooling and also on polarization gradient cooling now. So for ERT cooling, you need a 3-level system, and I think Dietrich Leibniz showed you the description of ERT cooling in terms of rate equations describing the cooling process. Here I want to highlight once again the important features of ERT cooling. So if you have now 2 ground states in this lambda configuration that couple to an excited state, and you choose the detunings from the excited state such that both lasers have the same detuning, then you will pump an ion that is fixed in space into a dark state, which is a superposition of the 2 ground states. And if you change the detuning of one laser and keep the other one fixed, and measure the fluorescence emitted by the ion, which is the same as measuring the upper state population, then you will find the line profile that is shown here on the right hand side. And what you see here is one resonance that corresponds to having maybe this weaker laser here becoming resonant with the excited state E, and then you have what is called a dark resonance, where the fluorescence vanishes as soon as the detuning of laser 2 equals the detuning of laser 1. And then you have another feature, which is a bright state, where the fluorescence increases quite dramatically, but over a fairly limited cooling range. And this feature corresponds then now to coupling the state G2 now to a dress state that results from the interaction between the state G1 and the excited state that is dressed by the laser light of the laser number 1. And the question is now, what happens if we do not consider an ion that is fixed in space, but instead an ion that is free to move in a trap, in a fairly confining trap? And in that case, now here you see once again this absorption profile in a bit more detail. It is possible now to set the lasers such that you suppress the excitation on the carrier transition, which would otherwise occur if it wasn't for this dark resonant condition. And if you remember the lecture by Dietrich Leibfried, then you might remember that what one wants to achieve is a good absorption on the red vibrational sideband, and as compared to the absorption that you have on the blue sideband and on the carrier transition. And this is exactly what you achieve here. So the excited state population goes up if we could detune the laser number 2 just by a little more. And if you now tune the coupling strength of the laser number 1 such that you create a dress state that gets shifted by an amount that equals just the oscillation frequency of the mode that you want to cool, then it means that even if the second laser now is tuned to the same detuning as the first one, then you can make use of this coupling to the stress state by a process where the missing energy now is provided by the ion motion. And so now you have a strong absorption on the red sideband, you have very weak absorption on the blue sideband on the carrier. And so the atom in the dark state cannot be excited in the carrier transition, but it can be excited by a red sideband process if you make this narrow bright resonant with the sideband transition. And this is something which enables then ground state cooling. And now this scheme is very interesting from an experimental point of view, because it enables you to take a level system and now tailor the properties of this level system to make it ideal maybe for for your experiment in terms of the parameters that you can set in this way. You can control the position of this bright state by having control over the intensity of the stronger light field, which pumps population into the second level. And you can control the width of this bright resonance by playing around with the detuning that both lasers have from the upper state. And in this way, you can suppress spontaneous emission from this carrier absorption, and therefore, in principle, you get better performance than by a usual resolved sideband cooling scheme that involves just 2 levels. You can have control over the absorption profile, and it is possible now to carry out ground state cooling on a dipole allowed transition as compared to, for example, a dipole forbidden transition or a 2-photon transition, where you usually need much more laser power for carrying out the laser cooling process. And finally, the frequency stability of the cooling laser is not very critical, because both beams can be derived from the same laser, and it is possible to achieve fairly high cooling rates. And this works in experiments quite well. So this is an example where you can see a 9-ion crystal with the spectrum of a 9-ion crystal, where on the left-hand side you have the red sidebands of all all 18 transverse modes of motion of this ion crystal. Then in the center you have this carrier transition, which has this stronger coupling to the laser than the sidebands. And on the right-hand side you have the blue sidebands. And when you compare the spectrum after Doppler cooling to the spectrum that you have, if you EIT cool the vibrational modes of motion before probing the spectrum with a laser pulse, then you can see that these red sidebands all are gone, which is a signature that the ion is in the ground state, or at least close to the ground state. And here it was possible then to cool these 18 vibrational modes of motion using a single laser pulse, even though they are spread out over more than a megahertz in frequency space. And it's possible to analyze this even further, and there's some data here which show you the cooling dynamics that you have in order to show that you have a pretty fast cooling scheme. And so here are measurements which I don't want to describe in detail, which provide us with access to measuring the distribution of phonons over the motional states after a given cooling time. And you see that you find the expected thermal distribution of motional states over these phonon states, and that this at the mean phonon number rapidly goes down and saturates after a few hundred microseconds of laser cooling. Now, a complementary scheme is polarization graded cooling of ions, and for this you once again need a multi-level cooling system, and a convenience scheme is a scheme where you have two ground states and two excited states. There are other configurations that are possible. And what is being done now is to excite the ions once again with a blue detuned light field. But in this case, you have a pair of counterpropagating laser beams with crossed linear polarizations. And this configuration produces a polarization gradient that has been used for a long time in neutral atom experiments for suboptical cooling, and has been used only much more recently in trapped ion experiments. And the idea is that you can see that you have now positions at which the light is plus and minus circularly polarized. And so this means that there are certain locations in space where there's just the red laser field that is shown here, the plus circularized one that couples the ground state G1 to the excited state E2. And in other locations, you have the blue light field. And now there are two effects that need to be considered. One is that you get now a spatially dependent optical pumping rate, because there are some locations where the ion state, ground state G1 gets pumped out and the population gets pumped into the state G2. And in other locations, the opposite happens and the population gets transferred from G2 to G1. And secondly, you also have position-dependent light shifts, because the light fields here are detuned from the atomic transition, and therefore you obtain light shifts that depend on the intensity ratio of these, or on the difference of intensities of these two laser fields. And so for the two ground states, you see that you have then now a periodic modulation of their energies. And this periodic modulation means now that in combination with the trapping potential, you get now a trapping potential that depends just only slightly, but still it depends a bit on that is slightly different for the ion being in the ground state G1 and the ion being in the ground state G2. And this is what I sketched here on the plot on the right-hand side. If the ion is in state G1, you have a harmonic potential that gets slightly displaced to the left. If it's in the state G2, you have a harmonic potential that gets slightly displaced to the right. And at the same time, you have now pumping rates that in the center are the same for both states, where both light fields have the same intensity, but that differ to the left and to the right. And this means that now you start favoring processes which are sketched here in this plot, where the ion motion, motion gets transferred into potential energy, where the kinetic energy gets transferred into potential energy, and then with a higher probability you go from this point into the other potential, where the potential energy is lower than in the reverse direction. And then at some point you get you get a normalization process, and you can use rate equations to treat this process. And what you find is that if the difference of light shifts is made equal or roughly equal to the oscillation frequency of the ion in the trap. You get an optimum cooling, and with this you can cool close to the ground state. You cannot really ground state cool, but you can cool close to the ground state and with a very high speed. And that is something which is shown here, at least experimentally, not in a qualitative way. But you can see here are once again spectra of the vibrational modes of motion of a 22 ion string. And so on the right hand side you have the red sidebands, on the blues, on the left hand side you have the red sidebands, on the right hand side you have the blue sidebands. And here the fluorescence was measured in a spatially resolved way by using a CCD camera, and this which explains the form of this excitation profile, because the lowest frequency modes that you have here correspond to modes where most the ions in the center of a string are excited, whereas the higher frequency modes here are modes where all ions get excited. And if you have a Doppler-cooled ion crystal, you can see both the red and the blue sidebands. After polarization gradient cooling, the coupling becomes anisotropic, which means that all of these modes are cooled at least pretty close to the ground state. And this becomes obvious also if you try to excite the ion on the carrier transition after such a cooling process. In principle, if the ion is well localized in the elliptical regime, then the coupling strength that you have does not depend on the motional state. However, if the ion is not well localized on the length scale of the laser, then this statement is not true. Then you can see that there's a dispersion of coupling strengths when you couple the laser and the ion, and therefore Rabi oscillations that you can drive on the ions quickly damp out if you average over many different experimental realizations, where the vibrational mode numbers might be different from experiment to experiment. As soon as you have polarization gradient cooling, you see that in the lower plot these oscillations persist for a long period of time. Yeah, I think that's all I wanted to say about laser cooling. Now let's go on about with experiment with long ion strings. What is it that we need? So first of all, we need, as mentioned already, very anisotropic potentials to produce these ion strings in the first place. So for example, if you have a 50 ion crystal, then you might need a trapping potential along the direction of the crystal, which is just barely above 100 kilohertz, whereas in the transit directions you need confinement of maybe 3 megahertz in order to keep the ion string linear. In such a potential, you can now start an experiment where in the first step you want to laser cool the ions, and typically this would be done by first Doppler cooling the ions into the elliptical regime where they are fairly well localized, and then you can maybe decide to sideband cool all transverse modes of motion close to their ground state using either resolved sideband cooling or ERT cooling, and it might be of interest to polarization gradient cool the axial modes of motion to sub-Doppler temperatures in order to control these modes as well. Secondly, we want to prepare the electronic state of the ions in a pure quantum state, which can be achieved by optical pumping. And then the important next step is the coherent manipulation of the ions quantum state by laser pulse. And I will spend more time on that. But I think first I want to mention that, we also need to carry out quantum state measurements by spatially resolved fluorescence measurements with a CCD camera in order to read out the quantum state manipulation that was induced by these laser pulses. Now, how do we measure and control single ions? By spatially resolved fluorescence, we can detect the individual states of ions. So here, for example, you have all ions in a state that couples to the laser that probes the ion's fluorescence, and so all ions appear bright. And this might be maybe, if you use a spin language, maybe a spin down state. And then we have a focused steerable laser beam that enables coherent single spin manipulation. And such a beam could be used now, for example, to coherently transfer the state of one ion from this fluorescing state into a state in which the ion will not fluoresce when probed with the laser pulse used for quantum state detection. And then you would take a picture where all the ions are bright except for one that seems to be missing. But of course, we know that it is not missing because otherwise the equilibrium positions of the bright ions would not be the same. And in order to really have control over all single ions in such a string, you want to make the laser beam steerable, which can be achieved by, for example, electro-optics or acousto-optics with fairly short beam switching times. This might be of interest now for preparing an interesting input state. In this case, maybe a few ions were transferred to a different quantum state. Now so you see that in this way we can measure now the state of individual ions, but what we can also do is to measure spin correlations, because we can really take single shot fluorescence measurements as the ones that you can see here, and then correlate the outcome of measurements on different ions in order to measure correlation functions. But of course, we would like to measure also other kinds of correlation functions. So these are correlation functions that are carried out in the energy basis, where I say I have one state that is labeled spin down, the other one I label spin up. But of course, we might be interested also in measuring in a different basis. So in this picture that you can see here, maybe we would like to project onto coherent superpositions of these two basis states, spin down plus spin up or spin down minus spin up. That is, we would like to project onto the eigenstates of the sigma X Pauli matrix. However, we only have the fluorescence measurement as the natural measurement for detecting quantum states of the ions. And in order to carry out measurements in different bases, what we need to do is to coherently rotate the states onto which we would like to project onto the states in which we can carry out the measurement. And for this, coherent laser pulses are very useful, because you can see that, for example, if we have a laser pulse that corresponds to a pi/2 pulse that maps then the eigenstates of sigma X onto the eigenstates of the sigma Z Pauli matrix, on which we can carry out the measurements. You see that if we apply this operation prior to a quantum measurement, then instead of measuring now sigma Z, we measure now the sigma X operator. And this enables us then, if we do this on different ions, enables us to measure in principle any correlation functions between the ions that we are interested in. Now, let's see how long did I talk so far? I think I'm halfway through, so this might be maybe a good time now for questions.
Hi. So the first question is actually from Noah, and she's asking, what do you mean by decoherence induced by the ion motion?
If you have an ion that is fixed in space that interacts with a laser pulse, then it means that this ion samples or sees the electric field at a particular position in space, the electric field of the laser. And if on the other hand, the ion is moving back and forth with a different amplitude, then the laser appears phase modulated in the reference frame of the ion. And if you have a state where the ion is not in the ground state, but in a thermal state, then you have a coupling that is not well defined. And this induces then decoherence in the laser-ion interaction. So this would be one example of decoherence induced by the ion motion.
Okay. So the second question is by Ansuman, and he's saying, in solid state system, we try to prevent decoherence by using pulse protocols. How effective are these pulse protocols in case of ion crystals?
Yes, I would say that these are used more and more in trapped ion experiments. So there are quite a number of experiments that use a kind of dynamical decoupling by carrying out repeated pi pulses that shuffle the ion populations between the two qubit states around, and that help to make the experiments more robust against some sources of noise.
Then there is a question by Mohesh, who is asking, is there any instability due to differential light shifts in sideband cooling process? Instability due to differential light shifts in the sideband cooling process.
I don't, yeah, I wouldn't know what kind of instabilities there might be. So yeah, typically I think we're not too concerned about decoherence or maybe fluctuating parameters in these laser cooling processes. They prove to be quite robust.
And he's also asking, what is the precision of AOD technique? AOD is probably acoustic devices that uses to move your this beam, which is imaging the ions.
Yes, yeah. So we use acousto-optical deflectors for deflecting an ion beam so that we can quickly change the direction of an ion beam from one ion to another ion, and so the technique is basically the same as also used in acousto-optical modulators, where you have some crystal that is driven by some piezo driver that creates a high frequency acoustical wave in the crystal that modulates the refraction index of the crystal, and then you have a running wave of a modulated refraction index on which you can they can use for diffracting the laser, and this results then in an angle change of the laser beam and also in a frequency change of the laser frequency that is equal to the radio frequency that was applied. And that is something that we use, for example, for fine control of the laser frequency of the pulses that interact with our ions. Because the laser itself is very frequency stable, it is stabilized to some external reference, and then we would like to be able to change the laser frequency in a controlled way over a range of a few 10 megahertz. And we would also like to be able to control the laser phase of one pulse with respect to a previous pulse. And that is achievable by using radio frequency pulses that transfer then the characteristics of the radio frequency pulses to the light field via acousto-optical modulators.
Okay, I have one question actually. So let's say for single ion, which subdoppler cooling technique will be more efficient, like EIT or sideband cooling? Because you don't have any normal modes of vibrations and so on.
Yeah, I would say EIT cooling is always better in the sense that if you would like to achieve low temperatures and you're maybe not so much concerned about the cooling range that I mentioned, then you can use a scheme where the laser detuning is very large compared to the decay rate of the upper state. And in this case, you get a cooling range that becomes more and more narrow, and in this way it approaches what you have in resolved sideband cooling. But you will always suppress the undesired processes that arise from a coupling to the carrier transition that do not contribute anything to the cooling itself and only heat the ion. And so if you say, what is the lowest temperature I can achieve while having efficient cooling over a given range, then EIT cooling is always better than sideband cooling.
Okay, thanks. Yeah, so there are no more questions at this moment, so maybe we can go forward with the remaining of the talk. Okay, good. Then let's continue with entangling interactions and trapped ion experiments. And so just as a brief reminder, I mean, maybe I should have shown the slide a bit earlier on. So there are, if you have a single ion and look at trapped ion laser interactions, then there are two quantum numbers that matter. One describes the internal state of your ion, and if you have just two levels that are relevant, then this might be now denoted by spin down and spin up. And in addition to that, you have the Fock states describing the motion of the ion, the quantized motion of the ion along one direction in space. And these are labeled here 0, 1, 2, and so on. And by making the laser frequency resonant with the atomic transition frequency,
you have the carrier transition, and this carrier transition is accompanied by a red and a blue sideband. And these sideband correspond now to transitions where upon excitation, you either reduce the vibrational quantum number by 1 unit or you increase the vibrational quantum number by 1 unit. And now what one can do is to make use of a bichromatic coupling. That is, you, instead of working with a laser that carries just a single frequency, you have a laser that carries two frequencies, one which is equal to the atomic transition frequency plus the oscillation frequency of the ion in the trap, and the other one equal to the transition frequency minus the oscillation frequency of the ion in the trap. And then you have this kind of James Cummings and anti-James Cummings coupling at the same time. And you can see here, once again, in the lower plot, that whenever you go from the spin down to the spin up state, which is described here in the Hamiltonian by the Pauli X matrix, you either reduce the vibrational quantum number by 1 unit or you increase it by 1 unit. And so this process is then described by the sum of a annihilation and degradation operator of phonons in your trap. And this is now a very interesting process for entangling a pair of ions, and was first suggested about 20 years ago by Anders Sørensen and Klaus Møllmer. If you apply this kind of coupling to a pair of ions, and in this example, there is one harmonic oscillator that is off-resonantly excited, as you will see in a moment, that mediates a coupling between the internal states of qubit 1 and qubit 2. And this is how it works. So this is a simple scheme where we have now to consider 4 electronic states that can matter. So both ions can be in state spin down, one of them can be excited, or the other one, or both can be in the excited state. And in addition to that, we also have the motional states of motion. And here I have just drawn the 2 lowest vibrational states of this quantum harmonic oscillator. And let's assume, for the sake of simplicity here, that we have an ion pair that is both initialized in the spin down state, and the harmonic oscillator has been cooled, has been prepared in the motional ground state. Now, what we want to do is now to apply this kind of bichromatic coupling in such a way that I have now a coupling where I have chosen the laser frequency slightly off resonant with the red and the blue sideband, in such a way that the sum of the 2 laser frequencies still matches twice the qubit transition frequency. But because of this detuning, the coupling to these vibrational sidebands is reduced. And so what I assume is that this coupling, that the detuning here is either big compared to the coupling strengths of to the Rabi frequencies of these 2 processes here. And in that case, you can see that we have here a kind of 2 ion, 2 photon transition that coherently couples the spin down to the spin up state in the case where this coupling strength here is not too big. So we can then calculate in second order perturbation theory and then a coupling strength, and then treat this level, this process here as in an effective way as a coupling between spin down, and spin up. And there's a similar process which I haven't sketched here that couples this spin down state to the spin up state, and which can happen either by the absorption of a blue sideband photon on one ion followed by a stimulated emission of a blue sideband photon by the other ion, or it can be started by a stimulated emission of a red sideband photon on one ion followed by an absorption of a red sideband photon by the other ion. And you can see here, it turns out that both processes have the same coupling strengths. And now if you apply such a laser pulse with the right timing, then it should be possible to stop this process midway, and in this way map the spin down state to the spin up state. And then you have, as these 2 processes have the same coupling strengths, you see now that this can be described by some effective Hamiltonian that is a product of the two Pauli X matrices. And so this looks like a magnetic interaction in an Ising model. And yeah, what is interesting about this scheme is that the coupling does not depend on the motional state, at least to first order. And that's something I would like to quickly discuss with you here. So if by calculating the coupling strengths here in second order perturbation theory. And I said that now there are two processes. So you can have an absorption on a red sideband of ion number 1. And in that case, the coupling strength is then proportional to the Lamb-Dicke factor times the Rabe frequency on the carrier multiplied with the square root of the number of phonons of the state you're starting in. And on the blue sideband, the coupling strength is usually, if you start in the same motional state, the coupling strength is bigger by you have here this factor square root of n+1 instead of square root of n. But now if you calculate now the coupling strength here, let's maybe first focus on this process where you have first a red sideband absorption followed by blue sideband absorption. Now you have this blue sideband coupling, but you start out in a motional state where you have just n-1 motional quanta. And therefore the coupling strength here once again is proportional to square root of n. And then you have to take the product of these coupling strengths and divide it by the detuning from the intermediate state. And then you have to add the second process where you have first an excitation on the blue sideband, where you have now a factor square root of n+1. And then the red sideband absorption now starts in a state where you have n+1 phonons. And therefore you get another factor square root of n+1. And you also have to take into consideration that now the tuning here from the mediating state has the opposite sign as compared to the other process here. So there's a minus sign showing up. And you can see that if you add up these two processes, then most of the coupling strength here cancels out, but there is a remaining part which is due to the factor +1 that you have here, and which gives then rise to a coupling strength which is proportional to the Lamb-Dicke factor times the Rabe frequency squared divided by the detuning from the intermediate state. You can see that this coupling strength now no longer depends on the vibrational quantum number of the initial state you started in. And that is an interesting feature because it means that you don't have to be, you don't need super good ground state cooling in order to have a well-defined coupling strength. So if in some cases the ions end up in the first excited motional state, you still should have the same coupling strength. That's from an experimental point of view, a strong advantage. Now, how does it look like if you apply this now to a pair of ions? And what you can see here is the population that is measured in where both ions are in the spin down state, which is the initial state, versus the duration of the laser pulse that induces the coupling. And you can see here that with increasing laser pulse duration, the population in the initial state starts to drop. At the same time, you see the population where both ions are in the spin up state go up. And after 50 microseconds, they meet here. And the population in the other two states where just one ion is excited goes to 0. And what you can see here is that so this is where you would expect to produce a Bell state. And if you carry out measurements, then you can see that this example here in 99.6% of the cases, the ions were in the desired state. And then you need some additional experiments to really prove that this is indeed an entangled state, because you also have to prove that you have phase coherence between this part of the superposition and the other one, and not just a mixture of the two states. And if you do this, then you find that it is indeed possible with such a scheme to produce a Bell state with a fidelity of something like 99.3%. And the fact that this scheme is independent of the motional state, at least to first order, is nicely illustrated here in the second plot, which shows the same experiment, but now instead of having a ground state cooled ion, the ions were just Doppler cooled. You can see here that now the population dynamics looks somewhat different, but after 50 microseconds, once again, you have basically all the population in the right state and very little population in the undesired states. And if you measure the fidelity of the state that is produced, then it has still a pretty high overlap with a perfect Bell state. What you also see by looking at these time traces here is that this simple picture which I presented to you so far, where I said that I can carry out a second order perturbation theory, is not quite right, because in between we have in these experiments substantial population in the intermediate states. So here this population can only be explained if you assume that here the vibrational quantum number has increased by 1 unit, but interestingly it vanishes at the right time. And I would like to spend a bit more time on explaining to you why this is so. And for this, I want to talk about geometric phases as another way to understand this Möller-Sörensen gate, but also related trapped ion quantum gates. And I first want to briefly talk about the driven harmonic oscillator in phase space, and then about the driven harmonic oscillator where the coupling becomes dependent on the qubit state. So if you have a classical harmonic oscillator, you have the phase space trajectory of an oscillator. Here is just a circle, and where the radius tells you something about the amplitude of the motion. Now, what happens if I start to resonantly excite this classical harmonic oscillator? Then in phase space, I will increase the amplitude of the oscillator's motion more and more, which corresponds to this spiral in phase space. And if I have a drive which is slightly out of resonance with the oscillation frequency, then I will excite the oscillator's motion more and more up to the point where the drive is high out of phase with the oscillator, and then I will de-excite the motion again, and then this process starts over and over again. Now, in order to have a simpler picture, it's useful to go into a rotating frame to get rid of this rather boring circular motion, so that now the circular motion here on the left-hand plot just turns into a fixed point, and where the spiral becomes then just a displacement along a particular direction in phase space, which is linear, and where the off-resonantly driven harmonic oscillator now gets converted into a motion where the oscillator reaches after some time its maximum amplitude before it returns to its original state again. And now this description completely carries over into the quantum case. Now, in that case, I have to introduce some phase space where I have maybe done the different quadratures here that I have, and where maybe I have a Wigner function or something like this, which describes my emotional state that I consider. And so what happens? What kind of Hamiltonian do I need to realize these different terms? So if I have a resonantly driven harmonic oscillator, then what I want to have is a resonant coupling between adjacent Fock states. And if I want to have an off-resonantly driven harmonic oscillator, then I have here time-dependent factors in front of the annihilation and degradation operator that enter the description. And I have a time-dependent Hamiltonian. And for this driven quantum harmonic oscillator, it's very simple, straightforward to calculate the time evolution by describing it in this interaction picture, which I just introduced to you. And then if I want to look at the time evolution and I want to calculate the propagator, then I have to slice up my time evolution into small pieces delta t, and then I can make use of first of all of the commutation relation between the annihilation operator and degradation operator, which is at the basis of of the rules that you have for these displacement operators in phase space, which are described by such an exponential term, which enable you to carry out a product of two displacement and convert it into a single displacement operator by making use of this general Becker-Campbell-Hausdorff formula. And what you find, if you follow this procedure, is that when you have this product of displacement operators, then you have a displacement which is the sum of the two displacements, but you also get another factor which is just a phase factor, which is given by the displacements here in phase space that you try to add up. And when you do this with with displacements which are described here by this off resonantly driven motion, then you see that you have this circle in phase space. But in addition to that, and this is what you don't see directly from this phase space picture, you have here now a phase factor which shows up. And this phase factor then starts to become important as soon as you go from this simple off resonantly driven quantum harmonic oscillator to an oscillator that has some state dependent coupling. But let's first have a quick look at what it means. So if I have now my oscillator here and I transport it now on this trajectory in phase space, then the quantum state returns to its original state, but it gets multiplied by what is called a geometric phase, which is set by the area which is enclosed by this trajectory here. And this is an irrelevant global phase if you don't have anything to compare it to. But it would be very interesting if you could now have maybe two quantum states that undergo here some evolution in phase space, which is not the same for one state in the other state, such that both states pick up different geometric phases. And then you see that now you have some interesting relative phase, which depends on the trajectory here that is taken by the two states. And for this, which becomes measurable. And for this, what we need to have is a state-dependent force. And this state-dependent force can now be engineered by having exactly this kind of bichromatic excitation. Because now what I have plotted here is now the case of this Murphy-Jorgensen gate, where the lasers are detuned from the intermediate states in such a way that the sum adds up to twice the qubit transition frequency. And you see that now we have here a Hamiltonian where the coupling to the motional state is described by this off-resonant excitation of the motion. But you also have this operator sigma x, which means that the coupling that you have now depends also on the electronic states of the ions. And importantly, if you have now this Hamiltonian that you apply to two ions at once, you can have different kinds of couplings depending on the internal states of both ions. And that is what I want to show you here. So once again, I have this circle in phase space, and the phase factor that is picked up depends on the area that is enclosed. And now, what happens if I prepare my ions both in an eigenstate of the sigma x operator? Then I can effectively replace this operator here by its eigenvalue when it acts on this electronic eigenstate, which would be in this case +1 +1, and then I have this trajectory in phase space. If both ions are in the other eigenstate, so which would be spin up minus spin down, then I have here an eigenvalue of this eigenstate of -1, and I have a sign change, which means that instead of first going to the right, I have a trajectory which goes to the left and also returns here to the origin after a certain amount of time. And I have the same amount of area which is enclosed here, so both geometric phases are the same. But if I have now eigenstates where one ion is in the +1 eigenstate and the other one in the -1 eigenstate, then you have a cancellation of the force, and there is no force acting on the motional state at all. And therefore, the phase that is picked up is just 0. And you can see now that I have now a phase, a geometric phase, that depends in a nonlinear fashion on the internal states of both ions. And this is what makes the gate entangling. And with this description, you also see that the requirements by the second order perturbation theory are a bit maybe too harsh in the sense that you don't necessarily have to demand that the coupling is much weaker than the tuning. So you can afford to have excursions in phase space which intermittently are large if you stop the operation at the time when all the parts of your superposition return to the original state which happens at a time which is the inverse of the detuning that you have chosen from the intermediate state. And in this way, you can then have spin interactions that between either a pair of ions or between many ions. And so far I talked about the Murman-Sørensen gate, but this is not the only entangling interaction that is available in trapped ion experiments. There is, what other options are there? You could say, can I reduce my ion-ion distance to approach the boreas? This is clearly impossible. One can make the ions bigger by going to Rydberg atoms, as in Markus Henrich's experiments. Or you can use these external fields for engineering state-dependent forces. And the spin-spin interaction mediated by a Coulomb interaction is one thing that one can use. And so in this case, it is it can be the laser that induces absorption and stimulated emission, and in this way transfers momentum from the light field to the ions. But another approach is also to make use of magnetic field gradients that produce position-dependent Zeeman shifts. And there are, I would say, two different approaches for doing this. You can think of having now a trapping potential and having a magnetic field gradient that shifts one qubit state in space in a different direction than the other qubit state. And then once again, you get a state-dependent potential where you can see that now the energy not only depends on the position of the ion with respect to the trap, but also on its internal state. And so there you have a spin-dependent force, which if the gradient is static, does not have any time dependence, but you can then make use, for example, of microwave-induced spin flips to have a coupling to the vibrational state that depends on the electronic state the ion is in. And then there is in addition to having this static field gradient, which you can use for then engineering also something like effective spin-spin couplings between the ions, you can also put ions into an oscillating field gradient. And then you have the very same mathematics as for the Murman-Sørensen gate, just maybe with in a slightly rotated basis, where you have an off-resonantly driven harmonic oscillator using a force that depends on the electronic state of one ion or of a pair of ions, which then gives rise to some effective interaction that involves only the operators describing the electronic degrees of freedom of the ion. And so in this case, you also then have a geometric gate that is induced by these interactions. And another geometric gate that is induced by lasers is a gate I want to briefly mention, which is called the conditional phase shift gate, where you have spatial light shifts that are induced by an off-resonant coupling to a standing wave. And so the idea is if you have a standing wave that is very off-resonant to some atomic levels, then you can achieve light shifts which are opposite maybe for the two qubit states that you're interested in. And so you have here now one standing wave, and for if the ion is in one state, and maybe a standing wave with the opposite sign here, or which is phase shifted in space if the ion is in the other qubit state. And by now working with a moving standing wave, which you can achieve by detuning the frequency of one laser with respect to the other counterpropagating laser, you can once again turn this into a time-dependent Hamiltonian that once again induces a coupling that can be described by these geometric phase gates. So this is a graphical representation of the standing waves moving over the position of the ion. And so this was one of the one of the first gates that has been realized with ions with a great success, which was done in the group at NIST. By now, the quality of these gates has further improved, and so the best gates now have a gate error, if you quantify this in terms of the fidelity of Bell state that can be produced, which is on the order of 99.9%, and both these sigma Z gates induced by light shifts as well as Murman-Sørensen gates have been shown to be very, very good for entangling a pair of ions with very high quality. And very recently, this was also matched now by this microwave approach, where the sigma z gate also has shown gate fidelities that are comparable with the best gates produced by laser lights. I have to check how I'm doing in time. I think I have maybe a few more minutes, but we can also use this for maybe for questions. I don't know what you prefer. Would be nice to have a bit of feedback on this.
Yeah, so there is a single question at this moment from Soumoranjan. So he's asking, can you please compare quantum noise and quantum decoherence in ion string qubits and photonic qubits?
Oh, this is a a very very wide question, I would say. Yes, I would say ion qubits and photonic qubits have complementary strengths and weaknesses, in the sense that, I mean, photons couple very weakly just to the environment, and in this sense they're great for being transmitted over large distances and for maybe building quantum networks. Whereas the strength of ions is that it's hard to have to transport them over large distances, but you have a very good control over the ions, and you can create them deterministically, and you don't have to rely on probabilistic procedures for example, entangling a pair of photons that otherwise would be very hard to couple by coupling it to yet another medium that might induce effective photon-photon interactions.
And there is another continuing question by him. He's asking about scalability of trapped ion qubits over other systems like NV centers and so on.
Yes, and that's something I want to discuss in the upcoming slides.
Okay. Yeah. So maybe then we can continue.
Okay. Then I think I will quickly go over the next few slides. I just wanted to show you that this kind of entangling interaction can not only be applied to just a pair of ions, but you can also apply it, for example, to 4 ions. And it turns out that in this way you can produce GZ states, and it works if you with more and more ions. And you can see that then in such experiments GZ states have been produced. This was 10 years ago with maybe a fidelity of 80% if you have 8 ions, but more recently there are similar experiments having demonstrated up to 24 ions in a GZ state with a fidelity that was not great, but given the huge size of the state space that is available, I think it's still quite impressive. About scaling up to larger numbers. What can one do? If one just wants to have a fairly small number of ions, you can now, for example, combine interactions where you have global entangling interactions that couple to all ions at the same time with some local interactions, and you can try to build up then some for example some quantum gate operation like the Toffolo gate in terms of these elementary operations. And in current experiments, with maybe up to 11 qubits, people have demonstrated that you can concatenate maybe 100 gate operations and have even hundreds of pulses in order to transfer the ions into different states. But clearly, this approach might work if you have 10 or maybe 20 quantum bits, but then you have to think about what can I do if I want to have more ions. And one approach that has been advertised by the NIST group for a long time is to build segmented traps, which are microfabricated traps with a large number of electrodes, which enable people to have more complex trapping potentials. So instead of having just a single harmonic trapping potential, you can think of having different trapping zones here in which you can trap subgroups of ions, where maybe some zones are maybe used for having interaction where the ions interact with laser beams, and other zones might be used for coupling ions to a detector. And then you could try to think of moving ions around in the trap and also joining different sections of ion strings, groups of ions, but in order to reorder them by by playing with DC voltages that set the confining potentials for the ions in these traps. And in addition, to being able to handle more ions, these microfabricated traps are interesting because you have smaller trap structures, and this provides also opportunities for adding more features to your ion trap and also for miniaturizing the experiments. And this is what has happened over the last couple of years. So nowadays there are, for example, surface ion traps where all the electrodes are in a single plane, which has advantages in terms of the fabrication process. You have traps where where you have monolithic segmented traps where you don't have to think about aligning different trap parts with respect to each other, which can be error prone if you have small structures. There are traps which have junctions like this one here, so where you can shuttle ions around and maybe split them up. There are traps which have demonstrated integrated photon detectors and also integrated optics. So for example, you can couple laser light into waveguides and then send it to an ion. And other traps have been built in order to have a good optical access from collecting fluorescence light, or having maybe thick metal layers where you can send in large currents, or having maybe trap technology that is CMOS compatible, or having backside loading. You have an atomic beam that might cover some parts of your ion trap, which would give rise to undesirable potential and so on. And so, for example, in terms of the optical connections of traps, Jonathan Holm provided me with a slide. They have done work on this, on integrating waveguides into their segmented trap structures, and this is what you can see here on the right-hand side. You have here the ion, which is trapped high over this planar trap, and where the upper electrode defines the trap electrodes. And then in the substrate itself, you have a waveguide that can send, they can guide light to the ions, and you have some Bragg gratings that have been written into these guides, which then send light out and focus it on the ion. And in this recent work, what they have shown is that this kind of technology is compatible with having high fidelity gate operations. And this is, I think, an interesting development, because if you think, for example, of putting an ion trap into a cryostat, which might have vibrations, then this way you might overcome the problem of guiding laser light to the ions without having disruptions by vibration in the cryostat. Other approaches to scaling up the ion trap quantum computer would be to couple ions to photons. This is something which, for example, has been pioneered by Chris Monroe and colleagues at the University of Maryland, where the idea is that maybe you can have an ion trap that couples to a high finesse mode of a cavity, and then you can have traveling photons that are either transmitted and coupled into another high finesse cavity, or where you have two similar setups where the photons then interfere and meet on a detector and are able to distribute entanglement then between ions trapped in different traps, which can be far apart. And with that, I think I'm at the end. I just leave you as a few references, which are also in the PDF version of my slides, which hopefully are soon uploaded on the website. And I thank you for your attention.
Thank you, Christian, for this fantastic elaborated talk on this ion trap techniques and etc. So let's see if there are a few more questions. I don't see anything in the chat box, but if you raise your hand or write something in the chat box, then we can take a few more questions.
Surely, can I ask something?
Yes, sure, go, Sourav, go ahead.
Hi, this is Sourav. See, we are in India, we are a very young community working on ion traps. So if you want to start in this direction of, let's say, going towards linear chains and quantum computing or simulation kind of things in the next, let's say, 7 or 8 years, so where does one start? I mean, what would be your suggestion on how to begin?
Yeah. I guess, yeah. I would say probably a good suggestion is to find a problem that is not maybe along the mainstream lines of experiments that are currently being conducted, since I think it can be quite challenging to catch up with existing groups, given that these groups might have an experience over the last 10 or 15 years, and where also maybe a large number of people are collaboratively working on the same topic, which provides certain synergies. I mean, should maybe to give you some perspective, so in the experiments that we carry out in Innsbruck, typically, so if we have a good team of people working on such an experiment, might be comprised of maybe having 2 PhD students, a postdoc, and a master student. But this team of people would have trouble doing the experiments if there wasn't the support of a larger group of people doing similar experiments. So we have, for example, control programs for controlling the ions, the radio frequency sources, and so on, that are shared between different groups and which are developed by groups, and so that not every single experimental team has to develop its own solutions. And the same goes for lasers, which in some cases are shared between experiments, which in the first place reduces the cost of the laser, but also the maintenance work for having stable lasers. So
thank you. Yeah, it's very helpful to know.
Okay, so I do not see any further questions in the chat box, neither there is any hand raised. So thank Christian for this nice talk, and see you tomorrow again at the same time for the second lecture.
Okay.
Okay.
See you then.
Bye-bye.
Bye-bye.
Thank you, both of you, Professor Christian Roos and Shubhodip. And the next talk by Martin Gerlin is at 8 o'clock Indian time. Till then, we have about 2 hours break. So see you at 8 o'clock. Thank you.